So again, Neuro.ZERO is a process architecture consisting of main MCU and accelerator MCU. So for the first main MCU, it is powered by battery. So it is always on, so it provides guaranteed execution of DNN. But on the other hand, accelerator is powered by an energy harvester. So sometimes it is on when there is enough amount of harvested energy, and sometimes it is off when there is no harvested energy. So which results in opportunistic performance improvement, which means that when the accelerator MCU is on, we have additional computational capability by having additional MCU available. In that case, we can improve the performance of DNN in a smart way based on application requirements and the energy level of the harvest energy. So here is an example. So when a man is walking, generating some kinetic energy, the accelerator, which is denoted, which is depicted as the green one during accelerator MCU, is turned on. In that case, the performance of DNN can get increased. But on the other hand, when man is standing, generating no energy, the accelerator MCU is turned off, and only the main MCU is executed. Because the main MCU is powered by battery, it is always on. In that case, we do not leverage the additional computational capability of the accelerator MCU because it is off. In that case, we can execute a little bit lower accuracy of DNN, but we can provide, execution of DNN all the time. Let me compare Neuro.ZERO against alternative architectures. So here, first, let's take a look at single MCU that is powered by battery. In that case, the single MCU can provide guaranteed execution, but it does not provide any computational capability increase because there is only one MCU. There is no second MCU. In the case of two MCUs, both of them are powered by battery. It can provide guaranteed execution as well as computational scaling, meaning that it has additional computational capability by having the second MCU. But the double MCU powered by batteries are not energy efficient because the second MCU consumes the system power because it is connected to battery. But on the other hand, the Neuro.ZERO achieves everything by having an accelerator MCU that is powered by independent energy harvester. Okay, the second part of Neuro.ZERO is multiple modes of DNN execution. So when the accelerator MCU becomes available, we can smartly leverage its additional computational capability to increase the performance of DNN, which is executed on MCU. The Neuro.ZERO provide 4 modes of acceleration. The first mode is Inference Speedup. The second mode is Inference Improvement. And the third mode is Multi-DNN Ensemble. And the last one is DNN Adaptation. Let me explain each mode with this example. So here is a delivery robot, and it has a system, the DNN system. The system's task is to recognize traffic signs. So the delivery robot can autonomously navigate itself on the road without collision. So let's take a look how Neuro.ZERO, the accelerator MCU that is powered by an energy harvester, can increase the performance of this DNN system. The first mode is Inference Speedup. So when the robot is running slowly, for example, 20 kilometers per hour, it will take 2 seconds to get to the stop sign. So the robot has to recognize stop sign within 2 seconds by executing its DNN. So DNN should be completed within 2 seconds. Otherwise, it cannot stop on time. So in that case, the main MCU would be enough. But when it runs faster, for example, 40 kilometers per hour, it will take 1 second to get to the stop sign. In that case, Neuro.ZERO can leverage the additional accelerator to speed up the execution to achieve the speed up, inference speed up. So the inference speed up is achieved by offloading some part of the DNN to the accelerator MCU. So here is DNN of which execution time is 100 milliseconds. But when accelerator becomes available by harvesting enough amount of energy, some part of the original DNN is offloaded to the accelerator MCU, and they are executed in parallel, which results in faster execution. So here, execution time is decreased from 100 milliseconds to 60 milliseconds. The next acceleration mode is improved inference. So when the robot is on the open road, it might be easy for the robot to recognize stop sign. But when it gets into a crowded road full of cars and pedestrians, and it might be more challenging to robot to recognize the traffic signs correctly, because there are so many stuffs, the cars or the occlusions and so forth. In that case, Neuro.ZERO can leverage the accelerator to achieve better recognition. So the goal of improved inference is to increase the inference accuracy by smartly leveraging the additional zero energy accelerator. So here, let's say there is a DNN of which accuracy is 80%, but when the accelerator becomes available, the original DNN is extended. Its size is extended by having multiple additional neurons, and they are executed in parallel, and finally it results in increased accuracy. So here accuracy, for example, is increased from 80% to 95%. The third acceleration mode is multi-DNN. So when it's a sunny day, it's easy for the robot to recognize traffic signs. So maybe we can only leverage the main MCU. But when it's snowing, it might be more challenging to recognize correctly. In that case, the robot might want to use a second camera to get correct recognition. In that case, the accelerator MCU can be leveraged to run a second DNN for the image generated from second camera. So there will be two DNNs. So the multiple DNN mode runs a different DNN that provides a second opinion for the task. So here the original DNN is always executed on main MCU. But when the accelerator becomes available, it runs an independent second DNN. And the output of two DNNs can be combined and assembled together to get better recognition. The last acceleration mode is DNN adaptation. So when the robot is in a place having familiar road signs where its DNN is trained for, it's easy to recognize traffic signs, and in that case we can only leverage the main MCU. But when the robot gets into a new place having totally different kind of traffic signs, in that case the recognition accuracy will be decreased. In that case, we can leverage the accelerator to adapt the DNN to the new traffic signs. So DNN adaptation enables retraining of the DNN on the accelerator by using only harvested energy. So here, main MCU keeps executing the current version of DNN, but whenever the accelerator MCU becomes available by harvesting enough amount of energy, it executes one iteration of training. But when the training is completed, the newly trained model is copied to the main MCU from since then on, the newly updated model is executed on the main MCU. So the newly trained model is supposed to provide better accuracy for the new traffic signs. By training on device, we can adapt the DNN to the new environment or new data set. So the last component of Neuro.ZERO is intermittent energy-aware algorithms. So because the energy harvesting pattern is unpredictable and unstable, so we propose energy-aware inference acceleration, which we named step-up inference. So when we extend the size of DNN, the amount of the acceleration here, extension is proportional to the currently available harvested energy. So when accelerator becomes available with little energy, we only extend the full number of neurons. But when we have more harvested energy, we extend more number of neurons, and we have even more, we extend more. So this energy-aware inference algorithms, enables a timely execution of, DNN as well as acceleration, regardless of the currently available amount of harvested energy. So next algorithm is skip-out training, which is energy-aware training. So similar to energy-aware inference, the amount of training is proportionally determined by the currently available amount of harvested energy. So here in the DNN graph, blue edges are wait to be trained, and gray dotted edges are wait to be skipped, not trained. And the amount of wait to be trained is proportionally determined by the current amount of harvested energy. So the energy-aware training algorithm guarantees the completion of one iteration of training, which consists of feed-forwarding and backpropagation, regardless of the amount of available harvested energy. So we implemented Neuro.ZERO prototype hardware, which consists of 2 MCUs and FRAM as a common memory space between 2 MCUs and sensors such as microphone. And we, based on the hardware prototype, we implemented 2 applications. The first application is traffic sign recognizer, and the next one, the next application is voice command recognizer that understand simple human voice commands such as yes or no. I want to share the evaluation results of traffic sign recognizer that is implemented with the 2 MSP430 microcontroller, where one is powered by a battery and the other one is powered by a solar panel. We use the GTSB dataset for the traffic sign dataset for our evaluation. So the first result is inference speedup. So here y-axis is clock cycle of the MCU, which means the execution time. So the lower, the better, the faster. So here is the main MCU without accelerator. And here is the result of Neuro.ZERO having different amount of harvested energy. The result shows that Neuro.ZERO can decrease the execution time almost 1.6 times. The next result is accuracy improvement. Here, y-axis is recognition accuracy. The higher, the better. And here is the main MCU without accelerator. And here is the result of Neuro.ZERO system having different amount of harvested energy. So the accuracy increases as more amount of harvested energy we have. And I want to emphasize that this accuracy increase is achieved by using zero system energy, because the accelerator is solely powered by an energy harvester. So the next result is a multi-DNN and Ensemble. Here again, y-axis is accuracy, and this is the result of first DNN that is executed on main MCU. And this is the result of second DNN, the different DNN that is executed on Accelerator. And this is the result of the ensemble result of the first and second DNN, which shows the better result than two individual DNN. The last result is DNN adaptation, which is about on-device training of DNN by using only harvested energy. So here x-axis is time, y-axis is training accuracy. So this graph shows that the training accuracy of the DNN that is trained solely on Accelerator by using only harvested energy. But its accuracy is lower than the GPU trained, the DNN, because it has, because the training, the batch size is only one, the mini batch size is only one, and then it also takes a very long time, like 100 hours, because energy cannot be harvested all the time. And the computational capability of MCU is very limited, so the training is very slow. So for conclusion, we introduced the Neuro.ZERO, intermittently powered accelerator that draws no system energy and accelerate the performance of DNN. We proposed energy-aware acceleration algorithms, which is step-up inference and skip-out training. We implemented two applications, a traffic sign and a voice command recognizer, that they demonstrated that their accuracy, the accuracy and the execution time is improved without using any system energy. And for the future work, we are considering having multi-core accelerator, because now we are only having one MCU for accelerator. Thank you.